So 4025 MAA mechanics, this is tutorial number 9, and we are going to solve, remember this tutorial was about the kinetics of translation. So let's start by solving exercise level 1. The 160 megagrams, so megagrams means 160,000 kilograms. So let's put here that the mass of the train is 160,000 kilograms. Travels with a speed of 80 kilometers an hour when it starts to climb the slope. If the engine exerts a traction force of 1/20th, so the force is 1/20th of the weight force, and the rolling resistance is 1/500th, so friction force. Let's call this R resistance, is 1/500th of the weight. Determine the deceleration of the train. So we want to find what is basically the acceleration of the train that will come out negative. So how do we approach this? Of course, it's always the case of doing a free body diagram. So let's say that the train is this one. More or less. We also know that the rise over run is 1/10. So we know this angle. How much is this angle? It's very, very simple to see that this angle here, alpha, is the arctangent of opposite over adjacent. Okay, but we can also say very easy that the cosine of alpha well, we don't need this really. So alpha is a number. This number here we can find later. And let's start by saying that the reference system is this one. So we have the y-axis oriented like this and the x-axis oriented like this. Why? Because this gives us a very, very good way of writing the equations of motion. So we know that the center of mass of the train has the weight force, which is equal to mg. The other forces are the traction force, F, and the resistance force, so the rolling resistance force, R. As you can see, this F and this R are completely along X, but we need a description for W, because W, the weight, is partly along this axis and partly along this axis. So there's a tiny. This one is W. So this alpha is this angle here. So this part is W cosine of alpha, and this part here is W sine alpha. Okay, you can just write the equations. Remember, this is Newton's second law, sum of forces. So the net force acting on a body is the mass of that body times the acceleration of that body. This is something you must remember. And so we can say quite easily that the sum of forces along the x-axis and along the y-axis are F minus R minus W sine alpha minus W sine alpha equals the mass of the train times the acceleration of the train along X, along the x-axis. And in the vertical direction, of course, I missed here. What did I miss? I missed the normal force. So there's the normal force from the train, from the ground, of course. So this second equation is just that the normal force minus W cosine of alpha equals 0. Now, the only information that we want is this one. Therefore, we'll just say that this is equation 1. This is equation 2. We don't need equation 2 because equation 2 just tells us how much is the normal force. But taking advantage of the fact that F is this and R is this, we can just say that from equation 1, we have 1/20th of W, 1/20th of mg, minus 1/500th of mg, minus mg sine of alpha equals mass times acceleration along x. So very, very, very nice description, because we can also observe that if this is the case, then the mass can cancel out everywhere. So we are left with a very, very, very good description here. They can say that the acceleration, finally the acceleration of the train along the x-axis is 1/20th minus 1/500th minus 1 g, because I can take g as a subject. G, G, and G can be taken as a subject. Oh, there's not one. This is minus sine alpha. Bad. So this is sine alpha. Okay, so this gives me. See, this gives me exactly the acceleration. Now, all of these are numbers. We just have to calculate these numbers. Let's find alpha first. Alpha is the arctangent of 1/10. So the arctangent of 0.1. So 0.1 arctangent is 5.7 degrees. It's 5.71 degrees. Let me say here that this one is 5.71 degrees. And so this is 1/20th minus 1/500th minus sine of 5.71, which is almost 1, almost 0.1, times g, 9.81. So this number is minus 0.505, minus 0.505 meters per second squared. There you go. This is the final answer. As you can see, it's quite easy. As soon as you do the free body, diagram, it's very easy to solve everything by looking at the information we have. All right, so let's do exercise level 2. Now, this is a bit more involved because you have two bodies that are connected to each other. So we have a 2 megagram truck. So that means that the mass of the truck, let's call this MT, is 2000 kilograms. It's traveling at a speed of 15 meters per second. Oh, one thing that we didn't take into account here is this is traveling at a speed of 80 kilometers an hour. As you can see, we didn't use this. Are there any reasons why? Well, we wanted to know the acceleration, only the acceleration of the train, which is a deceleration in this case. And the velocity does not fit in the free body diagram. Remember, the free body diagram only contains information on the forces, doesn't contain any kinematics quantities. That's very important. The velocities are never part of a free body diagram. Okay, the free body diagram shows all the forces acting on the body. From the forces come the accelerations, and the accelerations modify the velocity because it's a change in velocity. All right, so this 80 kilometers an hour was not required for the answer. Now, in this case, we have that the velocity of this truck is 15 meters per second. And now at this point, all the brakes are engaged, causing it to skid for a distance of 10 meters. So we know that it skids 10 meters before coming to rest. This is very important. We want to determine the constant horizontal force developed in the coupling C, this one here, and the frictional force developed between the tires of the truck and the road during this time. The total mass of the boat and trailer, so the mass of the boat is 1 megagram, so it's 1,000 kilograms. Okay, so let's do the free body diagram first, and let's see what do we know and what we don't know. Now, free body diagrams, we can, these are two bodies with two different masses. So let's do two free body diagrams, one for the trailer. This is the boat. And this one is the truck. Of course, the boat has its own weight, MBG. The truck has its own weight. So let's start with the boat. The boat feels its own weight, and of course, it's been propped up by a normal force on the boat. And we have a tension T, let's call it F. A tension, a force exchanged in this joint C. Let's call it FC. That's it. There is nothing else. On the truck, we have, of course, equal and opposite force here, because this is an internal force of the system. And the truck feels a deceleration force, sorry, a braking force. I'm trying my best to make it horizontal. There you go. FB, let's call this friction force, FF. And of course, it has its own weight as well. This here. MT, G, and it feels its own normal force. Okay, so this looks like we have everything that we need. All right, so let's start. What do we know? We know that, well, let's write the equations first. So I will write the equation for B. So this is for body B, this is for body T. So the equations on the x-axis and the y-axis. And so I need to define what are these x-axis and y-axis. So let's say that the y-axis is this, very classical, and the x-axis is this. In this case, I don't need fancy axes because all the forces are horizontal and vertical. So along the x-axis, I have that for body B, it's the towing force equals to the mass of the boat times the acceleration along x of the boat. In the y-axis, I have the mass. So I just say that the normal force on the boat is just the weight of the boat itself. Very easy. On this other side, I have along the x-axis and along the y-axis, I have a minus Fc. So minus Fc minus the friction force equals mass times acceleration x of the trailer. And y, I have that the normal force on the trailer is just the weight of the trailer itself. So these last two equations are useless, let's say. We don't need them, but we need equation 1 and equation 2. So what do we know and what we don't know? We know that we don't know this. So this is why this is one unknown. This is my second unknown. But then we also have 3 and 4. So it looks like we have 4 unknowns and only 2 equations. So something is missing. Well, one thing that is missing for sure is the kinematic relationship. So we are considering these 2 bodies in isolation in the free body diagram. And this is never, never, how do you say? You don't stop here, okay? You never stop here. So when you look at this in isolation and you look at this in isolation, you also have to find what is the relationship between these 2. Now, these ones are rigidly attached. Now, rigid connection, the rigid connection C at C provides the same displacement. Agreed? Because if the truck moves 1 meter, this boat moves 1 meter. So the same displacements. And so you can say that the displacement of the truck is equal to the displacement of the boat along the x. Let's call this displacement of the truck in the x direction is equal to the displacement of the boat in the x direction. And so if you differentiate this once, you get that the velocity in the x direction of the truck is the same as the velocity in the x direction of the boat. And if you differentiate this one more time, you get that the acceleration along x of the truck is the same as the acceleration along x of the boat. And this will be our equation 3. This is called kinematic relationship. This thing. Okay, so this basically connects the unknown number 3 with the unknown number 4. 1, 2, 3, 4. But we still have 4 unknowns and 3 equations. So what's missing? Again, Now, the last thing that is missing is that we have information on the kinematics of the entire system here. So we know that it starts with an initial speed v0 of 15 meters per second, and then it stops with a final speed of 0 meters per second after 10 meters. Okay, so we can just use knowing the kinematics of the trailer, of the truck, sorry, the truck T. We can say, remember this, remember that V squared equals V0 squared plus 2a s minus s0. So this equation here can be used to find the acceleration. Now in this case, this a is the acceleration of the truck along x. This s is this is the final s, which is 10 meters. This s0 is 0 because we start at 0. The initial speed is 15. The final speed is 0. So from this, we can say that axt, the acceleration along x of the truck is minus 15 squared divided by 2 times 10 minus 0. There you go. And this acceleration is, let me check, should be 11.25. So minus 11.25 meters per second squared. So this was my equation 4, basically. As you can see, my unknown is this one. And so now I have all the information I need. So I can now solve, finally, solve a system of equation 1, equation 2, equation 3, equation 4. And from equation 1, we find Fc equals something, something in newtons. From equation 2, we get Ff is something, something in newtons. And then we have that A of x, t is minus 11.25. And of course, Ax of b is also the same, because equation 3 tells us that these are exactly the same. This here. So finally solve this one. Okay, now this should be easy. Do you agree with me? Any questions? While I rearrange these things. Any questions? Doesn't look like we have any questions. Hopefully, this is a good thing. Okay. So let's do exercise level 3. We have an 800 kilogram car at B. So this, we're looking at this car here. So mass of B is 800 kilograms. It's connected to the 350 kilogram car at A. The mass of A is 350 kilograms. And it's connected by a spring coupling, for which we know that the stiffness of the spring is 600 newtons per meter. How do I know? It's here. Determine the stretch in the spring. So we want to find delta x if the wheels of both cars are free to roll, and if B is braking. Okay, so we know that the coefficient of friction of B is 40%. So we want to find delta X if free. And let me write it like this, delta X free. And delta X breaking. Where delta X is the elongation of this spring here. We also know that this is a 3-4-5 triangle. So let's take this angle alpha. And we know that alpha, well, we know that the sine of alpha, the cosine of alpha is 3/5. And the sine of alpha is 4/5. So this makes our equations a bit easier. Okay, so let's see what happens if both of these are rolling down freely. So first thing to do is the free body diagram of both things. So free body diagrams. So I have for cart B and for cart A. So for B, it looks something like this. Where you have this spring. And that's it. Yeah, that's it. And for A, it's exactly the same. It's just the other way around. So this is here. So the forces acting are, of course, the weight of B, which is equal to mbg. So let's call this mbg directly. It's the mass of B times G. And here you have the mass of A times G. This is the spring force. Let's call this Fk. And that's it. So this is in the case of free rolling. Now let's also apply the braking force here. And let's call this R. And then in order to see the free, so in order to study the free condition, we'll set R equal to 0. Okay, so we can do this analysis in the general case of the braking. And then if we set R equal to 0, we see what happens when it's free. So when it's not braking. So this saves you to redo all the analysis one more time with a different free body diagram. So you just want to be a bit smart about it. This R is, of course, mu k times n b. And of course, we also have the nb and na here. And the axis, let's say that this is the y-axis and this is the x-axis. And the same thing, this is the y-axis, this is the x-axis. Okay. So let's draw the equations. So remember the equations. Newton's second law is always the same. And so let's say that on the x-axis and on the y-axis. On the x-axis, we have Fk, which of course, since we know K, let's say that Fk is also K delta X. And this is also k delta x. Is a spring force. So we can say that k delta x minus mu k and b, and then we have to split, of course, remember we have to split this into its y component and x component. And this is the angle alpha. So this one is mbg sine of alpha, because it's opposite, and this one is mbg cosine of alpha. And of course, you also have exactly the same thing here. Because this is also alpha. Okay, so what's missing here? We accounted this, we need to account this one. So plus, because it's in the same direction of the x-axis, plus mb g times the sine of alpha. So sine of alpha, remember, we have it here, it's 4/5. So I will just say 4 divided by 5 mbg. And this is equal to the mass of B times the acceleration of B along the x-axis. And in the y-axis, we have that NB equals 3/5 of mg. Okay, so this equation will help us with this. So this NB is here. So I'll probably rewrite equation 1. Let me do the same for the other curve first. So let's say that in the x direction and in the y direction. Here I have minus k delta x now, because it's going in the opposite direction of the x-axis, plus mag sine alpha, which is 4/5 sine alpha, yes, 4/5. mag equals mass of A times acceleration of A in the x-axis. And NA, now this equation is truly useless because we don't need it for anything. 3/5 MA times G. Now this is a number. We know everything. Okay, so let me rewrite equation 1. This is equation 1, this is equation 2, and I will rewrite equation 1 by knowing this bit of information. This one is a number and this one is a number. Let's check how many unknowns we have. So we want to know delta x. So delta x is my real unknown. But I also don't know a of x of b and a of x of a. So again, this is another issue, is that we want to see what is the acceleration of this. Of course, as you can imagine, if this is if this is free, of course, both of these will go down at the same speed. And if both of these go down at the same speed, I'm expecting there would be no stretch in the spring because they will just follow each other and the spring will never be engaged. Whereas if this one is braking, of course, this is braking, this is not, so this will go faster, and so the spring will get engaged and it will stretch by almost 1 meter. So let's see how we do this. Let me write the equations first. So this is equation 1. So k delta x minus mu k, so minus 3/5 mu k mb g plus 4/5 mb g equals mb ax of b. And this is k delta x from minus k delta x plus 4/5 ma g equals ma ax of a. And this is equation number 2. Now, if you look at this, it's very easy to see that we can sum these two. We can easily sum these two. So in the free case, in the free case, mu k is 0. Remember, we have no friction. Say we have no friction, so this goes away completely. So in the free case, if I sum equation 1 and equation 2, let's see what happens. Let's see if I have. Okay. I end up with, so if I sum equation 1 and equation 2, this goes away. This is 0 already. So I have just this plus this equals this plus this. And remember, I told you that the accelerations are the same as well. So this is the other important bit, is that ax of b equals ax of a. So if you sum 1 and 2 in this case, you get that 4/5 of ma plus mb g equals equals ma plus mb times the acceleration. Let's take the acceleration of b because they are the same. And so as you can see, these two go away and you can find the acceleration and the stretch of the spring, of course, is 0. And it must be 0 because if you now find this number and you put it here, you find that this balances everything in this equation. So delta x must be 0. In the brake case, this is the equation. And so it's just very easy to see that you need delta x equals, so you just have to find delta x again. So you can find the force of the spring by saying then delta x equals, well, you just have to rearrange this equation really. Delta x would be a certain number of meters or millimeters in this case. All right, we have 10 minutes to solve this last one. We have a skateboard rider leaving the ramp at A with an initial velocity VA, which is unknown, at 30 degrees angle. If he strikes the ground at B, determine VA and the time of flight. So remember, this is just about kinematics and it's parabolic motion. So we have let's recall the equations of parabolic motion. We have the acceleration of this man is minus g. So this is the acceleration is, of course, in x and y. Acceleration in x is 0, acceleration is y is minus g. Then you can integrate once to find the velocities in x and y. Well, let's do this directly. So let's start by integrating, let's say integrating the accelerations to find velocities. So this is in the x-axis. So this is free falling. So the velocities are x and y. In x, it's just v0x plus a0x, sorry, plus a0x times t. So we don't have the x velocity, the x acceleration is 0. So this is just this v0, we called it va because that's the initial speed. So we have vax, and that's it. Vax is constant. In this case, we have vay plus a0y of t, which becomes vay minus gt, and this is linear. And integrating one more time, once more, to find displacements. We get along x and along y. This one is vaxt plus, so let me do this, s of x of t is vaxt plus s0x, which is linear. And sy of t is vay, sorry, this is, yes, vay t minus half gt squared plus s0y. Okay, so let's see what are these numbers. So this is parabolic, of course. Now we have the general expressions of all of these. We can see very easy that the initial, so s of 0, so sx of 0 is 0. So let's say that my reference system is this one. So S along X is 0, but S0 along Y is 1, because it starts 1 meter above. So this one is 0, but this one is 1 meter. So we know that VAX and VAY are these vectors, are these components here. So this is VAX, and this one VAY. And so we know that this angle is 30 degrees. So we know that VAX is VA cosine of 30, and VAY is VA sine of 30. So let's rewrite this by saying that Sx of t is VA cosine of 30, and that's it. And Sy of t is minus half gt squared plus VA sine of 30 plus 1. Now, the things that we want, we know that Sx of t and Sy of t at the final time, so when time is final, so at the end of the jump at time t final, we have that Sx of t final is, so at point B is Sx is 5 meters. And so 5 meters is also VA, I'm missing a T here, is 5 meters equals VA cosine of 30 times T final. And this is one equation in 2 unknowns. So this is my first, this is my second unknown. So the other equation is Sy at the final time is, of course, since it hits the ground, the y coordinate of this point is 0, which is VA sine of the, sorry, no, this is minus half g t final squared plus VA sine of 30 plus 1. So these are the 2 equations that I need. So let me put these. So these. And these 2 equations also have my second unknown and my first unknown. So this is 2 equations into unknowns. So I can solve this, solving equation 1, equation 2 gives me VA and T final. So VA is 6.49 meters per second. And this is the magnitude of the vector. And the time it takes is 0.89 seconds. Okay, any questions? I'm going to stop recording here.